Now, as we've stated before, centripetal force is a label that we give other forces that cause objects to go in circles. It's always pointing towards the center of the circle. Now, if you think about a car turning on a road, so there must be some force causing it to turn, because that force is going to point towards the center of a circle. Imagine with a road, if you will, extending those lanes on around, and if you keep going, of course, you'll eventually get all the way around in a circle. So any curve is actually a part of a circle. Now I have here a car, this is kind of a top view as a helicopter might be looking down, going 18 meters per second around a road. And here's a tree over here. And my question is the car going too fast for this curve, or is it going to be able to make the curve? And I made the curve have a radius of 92 meters. And so we're going to see, can it make it around the curve, or does it slide off and hit the tree? Now, if you're ever trying to determine what force is actually causing the centripetal force, ask, if this force, whatever force you're trying to figure out, is missing, what would happen? Specifically, what if this road were ice instead of actually being pavement? So slick of an ice that we actually had zero friction. Would the car be able to turn without friction, or would it continue on straight? And the answer is it would continue on straight. Without friction, cars can't turn. So the force that actually causes the car to turn is friction. Friction's what's pointing in. Check out this free body diagram here, rear view of the car. Normal force going up in the Y, force of gravity going down in the Y, and force of friction pointing into the circle. That's what allows the car to turn. Like I said, anytime you're trying to figure out, is that actually centripetal force, ask, what if that force is missing? If there's no friction, the car isn't going to be able to turn. It's going to slide off straight and unfortunately into our tree. Likewise, friction has a limited quantity. It doesn't go all the way up. The force doesn't continue up forever. In fact, we know an equation for friction. Force of friction equals mu times normal force. And if you need a larger centripetal force than mu times normal force, then you're going to end up going too fast. It's not going to be able to provide it. You're going to slide off. So the question I want to ask in this problem is this car going too fast at 18 meters per second for this curve? Can he make the turn? An easy way to do that is solve for the maximum velocity this car can go around the road. Now I'm labeling my x-axis to be into the circle and out of the circle. So my x-axis is going along like this, where my y-axis is going, up and down. Check out this rear view to get a good idea of that. So in the x-axis, sum of the forces equals ma, but what's actually happening here is centripetal force. The car is actually trying to go in a circle in the y-axis. So centripetal force equals mv squared over r. And the force that's providing that centripetal force is the force of friction. Force of friction is going to now be mv squared over r. And there isn't any other forces pointing into the circle or out of the circle. It's the force of friction that's providing it. I'm looking for v here, the maximum velocity that we can go around the circle based upon how strong friction is. And the maximum force that friction can provide is mu times normal force. So that'll be set equal now to mv squared over r. Now looking at this idea, I know mu. I'm given the coefficient of friction between the tires and the road. It's 0.75. I don't know normal force. I'm going to end up having to go get that. I don't know the mass of the car, and so generally what you find whenever you don't have the mass of the car is you kind of hope that the mass is going to cancel out. The velocity, how fast it's going to go around the turn, so I'm giving it maximum force of friction, all mu times normal force, taking friction all the way to the max, will give me the maximum velocity, and I'm told the radius, 92 meters. So really where I'm stuck is the normal force. I need to go get that. And just like in Newton's second law, normal force can be found from the y-axis, F equals ma problem. I have normal force going up and gravity going down, and the car obviously isn't accelerating into outer space or plunging down into the depths of the earth. So as is usual, whenever you're not accelerating upwards or down, and there are no other forces besides normal force and gravity in the y-axis, normal force comes out to be mass times gravity, and I can now substitute that in over here into the x-axis where I'm dealing with centripetal force, right? It's in the x-axis that the car is turning. So now I have mu mg equals mv squared over r, and thank goodness, look at this. I have an m in this term. I have the m in the numerator of that term. That means these m's will cancel, divide both sides by m, and they're gone. Now I have mu, the coefficient of friction, mu g, equals v squared over r. Now, I do want to point something out. This should make possibly a lot of logical sense to you. This is the centripetal acceleration. This would be the acceleration that friction could provide, if you will. Notice the lack of the m, right? We divided the m out. Now, I know everything to solve for v. I know the coefficient of friction, gravity, 9.81, and I know the radius. And whenever I work this all the way through, I come out with a turn of a 92 meter radius. You can go around average with the coefficient of friction 0.75. You can go around with a maximum of 26 meters per second. That's a little bit greater than 55 miles per hour. So this car is going to be perfectly fine. It's going to make the curve, not to go sliding off into the tree. Thank goodness. All right, some last thoughts that I want to go ahead and go back over just to make sure I point these out. Here, this was a two-dimensional problem. Friction was what was providing the centripetal force. Remember, centripetal force is just a label that we give to the forces that point towards the center of the circle, causing the objects to move in a circle. And a curve is a part of a circle here. So friction was what was providing it. The reason it was two-dimensional was because force of friction, what was providing it, breaks into mu times normal force, and I need normal force, which means I've got to go to what's happening in the y-axis for this car, up and down, right? So I go to the y-axis, I solve for normal force to substitute in. If you were just solving this yourself, you might not have thought about that to start out with. You might have gotten to the point where, okay, what if it's on ice, it would slide off, friction must be causing it to turn. So I'm going to have force of friction, mu times normal force, mv squared over r, and so then you're kind of left with normal force, and that's where I would expect the light bulb to come on of, oh, I need to actually go to the y-axis, the vertical in the car, to get normal force, just like you did in F equals ma. Last thing I'd like to point out here is whenever it comes to going around a turn, mass does not matter. Notice it completely canceled out. And then I guess actually my second last thing is this is a comparison problem. Remember, the question was, would the car be able to make the turn? That screams comparison. So you solve for something like here, we solved for the maximum velocity you could go around the turn and compare to the velocity that you actually were going 18 meters per second in this case, which is under my maximum, meaning the car would be able to make a turn. So always double check on your comparison problems.